Hello, everybody. How are you? Good evening, and welcome to our collaboration, our official collaboration with mathleague.org. This is actually a lot of fun because, as you know, we love to do questions with people who write good questions, and mathleague.org runs a lot of competitions that run throughout the year. And in fact, if you aren't participating in them, we strongly recommend that you do because these are a great way to stay in shape. Actually, they run a lot of competitions every year, and we're going to talk about the questions today, which are from qualifying round 6 at the middle school level. Now, something I want to emphasize. Our official collaboration with Math League is official. So in particular, we're going to be using their problems, and these problems are copyrighted. And so please treat them with respect. Don't just copy all of these problems everywhere else. We're working on this because we're very proud to be officially collaborating with them to try to solve some questions. Now, if you have never watched this live stream before, don't worry, you're not alone. Neither have I. Well, I guess that's obvious, but I think what I mean to say is I actually haven't looked at any of these questions before either. And the way I do the reason I do the Math League live streams and all of these solve live streams this way is because I want to show how you might try to think about a problem the first time when you see it. That's like one of the ways that you learn how to solve a question. And yes, somebody is asking, is this for 12116? That looks familiar. I think it is. But I actually only looked at it as middle school qualifying round 6. It's the one that just finished. Somebody said there's a random dot in the middle of the screen. Well, let's fix that. And the way we'll fix that is by starting the problems. Okay, what's this? I'm going to make it a bit easier for me to see by clicking on a button. All right. Sprint round number 9. What is the number of different arrangements of the letters of the word pam-pam-pam-appa? Okay, so this is actually legitimately a very hard question because it involves the hardest area of mathematics called counting. This is where I make a lot of mistakes. Good gracious, how many letters of every type are there? Well, how many P's? That's easy to count because they kind of look different. 1, 2, 3. 3 P's. How many A's? Oh, that's harder. 1, 2, 3, 4. 4 A's. How many M's? 1, 2. Okay. Any more letters? Doesn't look like it. Here's how I double check. First of all, I add these 3 numbers together, 2, 3, and 4, when I have 3 consecutive numbers, which means they separate by 1 each. The sum of 3 consecutive numbers is just 3 times the middle number. And so that's 3 times 3. The sum should be 9. Are there 9 letters here? That's 3, that's 3, that's 3. Looks good. So I think we have all of them. So now what I have to do is I want to know how many ways can I rearrange it. This is a combinatorics problem. And when you do this kind of combinatorics problem, you say, well, there's 9 things, right? If there's 9 things, the answer is just 9 factorial. That's the number of ways to rearrange 9 things. Well, that's correct if the 9 things were all different. But unfortunately, they're not all different. Well, actually, fortunately, because I don't want to multiply 9 factorial. And what you do to fix that, this is a live solve, so I don't have time to teach you and explain all of the different reasonings, even though I'd love to. But I'll just remind you briefly. There are 3 P's. Wherever they appear, like, look at this, pam-pam-appa. If all the 3 P's were like really different P's, because maybe one had a little curly thing here, one had a curly thing there, and one was straight, well, you could also have pam-pam-appa, where those 3 P's were rearranged in some other order but held their place. And there are 3 factorial ways that you could rearrange those 3 P's amongst themselves. Similarly, the 4 A's you can rearrange in 4 factorial ways, and the 2 M's you can rearrange in 2 factorial ways. Whenever I have something like this, the way I expand it is I say that's 9 times 8 times 7 times 6 times 5. I go up until the biggest factorial on the bottom, because the rest is just 4 factorial, divided by 3 factorial, 4 factorial, 2 factorial. Hooray! Now I can cancel the 4 factorial away. Next thing I'll do, 3 factorial is 6. I like canceling that away because there's a 6 on top. 2 factorial is just 2. So let's take a 2 out of the 8, and that leaves 4 here. Now we get to the second hardest part of this question, which is trying to multiply. Oh, somebody just said it's a song. Oh, that's really cool. Okay, I've learned something today. All right, so now I have to multiply these together. 9 times 4 times 7 times 5. What's the easiest way to do this? Well, I see a 5. I like 5. 5 times even numbers makes 10. So the 5 times 4 makes 20. I'm going to rewrite that as 9 times 7 times 20, because that was 4 times 5. That's good. 9 times 7 is 63 times 20. And multiplying by 2 is easy. You just double everything. And it looks like I got 1260. All right. Let's see if that's the right answer. Let's see. Is this Pemapa? The moment of truth. Yes, 1260 is correct. Pemapa. Okay, I'm not sure if that's what I was supposed to say, but let's go on to the next question. Question 11. Melody has 360 packets of gummy worms, 675 lollipops, and no candy bags. Oh my, that's a big problem. You got too much candy and no bags. She decides to buy the maximum number of candy bags such that she can divide the packets of gummy worms evenly across the bags and that she can divide the lollipops evenly across the bags. But each candy bag costs $1.20. How much money in dollars does Melody spend for candy bags? All right, so I need to have the maximum number of candy bars so that you can divide. That means I need the greatest common factor, right? Because I have to be able to divide. I need a factor of that and a factor of that. Oh, that's a common factor. So sometimes we call that GCD for greatest common factor, greatest common divisor. Many people use the same thing. GCD of 360 and 675. There are different ways to solve this. You can use something called the Euclidean Algorithm. Ooh, I actually already saw somebody asking, shouldn't it be LCM? Well, here's how you can think of it, right? So if you're wondering, should it be LCM or GCF or GCD? Well, the way I thought of this is I need to divide the packets, right? Let's highlight something. I need to divide the packets of gummy worms into something, right? So I need to be able to divide the 360 into smaller pieces. That means I'm looking for a factor of 360. And I also need to divide the lollipop, so I need to have a factor of 675. Now, when I look at this, I say, one way to do this is with the Euclidean algorithm, where you kind of subtract things. But because these numbers are so nice, my gut feeling is to do it in two ways, just to show you that the Euclidean algorithm is cool. But let's just do it the way that you might do it first, which is just like, let's factorize this thing, okay? So if I want to factorize 360, I need this. Okay, let's do this in two ways. Let's do first way, GCD 360 and 675. So I have a 360. Ooh, I'll tell you how I do this. So I'll do 360, and I have a 675. Sometimes I actually even just like factorize with factor trees. That's like 6 times 60. And the 6 I can pick apart into 2 times 3. 60 is 5 times 12, and the 12 factors into, I'm going to do this, 3, 2, and 2. Okay, so if I pull all of that out, now let's just go and, somebody said, what's the maximum number of bags? Someone thinks I made a mistake. So let's see. She wants to find the maximum, Okay, so I'm looking at the chat. I do want to answer your questions as you're going. If I want to have the maximum number of bags, that's why I have a G for greatest, right? So I'm really looking for a common divisor or a common factor, which is the greatest. So that's the maximum there. So we're all good. All right. So as we keep going, I've factorized out 360. So that means 360 is 2 to the third power times 3 to the second power times 5 to the first power, right? Because I have 1, 2, 3 many 2's. I have 2 3's and I have a 5. 675, how about you? Well, that looks like 25 times something. Do I dare to take the whole 25 out at once? Yes, I do. And so how I'm going to take the 25 out at once is that I know that 100 is 4 25s. So 600 should be 6 times 4 25s. That's 24 of them. But then I have an extra 3. That's 27. Immediately, when I see a 27, I say, that's a multiple of 9. Do I believe that this is a multiple of 9? I check by adding the digits. 7 plus 5 is 12, plus 6 is 18. That's a multiple of 9. Good, I didn't make a mistake. Now let's split them apart. 25 is 5 times 5. 27 is just 3, 3, and 3. So over here, the other number is 3 cubed times 5 squared. If you were watching my live streams earlier this year, I think maybe last week or the week before, we came across something like this before also. And the way you do a GCD, I now want to find something which divides into both of these. And so the GCD is just what you get if you take 2 to the smaller of the two powers, that's 2 to the 0, times 3 to the smaller of the two powers, that's 3 squared, times 5 to the smaller of the two powers, that's 5 to the first. And the reason is because if I want to have a common divisor, well then I can only be made out of 2s, 3s, and 5s. Don't try to grab a 7. 7 is no fun. You can't divide these by 7. But how many 2s can I get? Well, I'm stuck. There's a 2 to the 0 here, so you better not have any. But the 3s, I got 2 3s here and I've got 3 3s there, so I may as well grab 2 of the 3s. So the greatest common divisor is just all of those primes to the power of the minimum of each of those exponents. And here we get 3 squared times 5. That's 9 times 5. That's 45. And so my first answer is 45. I also want to show you the Euclidean algorithm. We don't have enough time to really prove why this works. Actually, I do that in the number theory class. But here, let's just do it. If I wanted to know GCD of 360 and what was the other? 675. I'm writing parentheses to mean that's the GCD of those two numbers. It's actually the same as if I went and took the first number, 360, and I take the second, the bigger number minus the smaller number, which is 315. Okay? The reason why this is true, by the way, is because, okay, here I am telling you why it's true. It's because somehow whatever divides both of these also divides both of those. Because if you divide both of these things, well then yeah, you divide 360. Yeah, that's one of them. And why do you divide the 315? If I divide both of these numbers, then I definitely divide their difference. So it goes there. So whatever divides both of these, divides both of those. And vice versa. Whatever divides both of these, divides both of those. See? It divides both of these. Yeah, of course, it divides 360. Why is it true that if I divide both of these, then I automatically divide 675? Well, that's the sum of them, right? If I divide both of these, I divide their sum too. Okay, that was a quick thing. In a proper number theory class, I'd explain it more slowly. But now let's keep going. If I want to do this, now I can do the trick over and over again. I can always subtract the smaller one from the bigger one. And so 360 minus 315, that's 45. Oops. 45 and 315. And now we will proceed to subtract and subtract and subtract. So 45, let's write more neatly. 45 and 315 minus 45 is what? 270. Okay, now we're going to have to keep subtracting. And actually what I see here already is if I kept subtracting the smaller one, I will keep subtracting, and I see that 270 is a multiple of 90. Actually, that means that 270 is a multiple of 45. So if I just kept going, I would eventually get to 45, comma 45. And you know what? What's the GCD of 45 and 45? Well, that's obvious. That's 45. Okay, so this is another very fast way to go and find the GCD of numbers without having to do the prime factorization. And we're going to propose the answer of 45. Oh no, it was 54. We screwed up. Wait a second. Now I'm looking at this. I'm guessing that there's a typo in the answer key that we put here. So I'm just going to overrule the 54 and say, I don't believe 54 because you can't divide 360 into 54s. Can you? Nah, you can't. You can't. You can't. Oh boy, you really can't divide 675 into 54s. So that's not. Oh no, we screwed up. Oh, I made a mistake. And now this is the other thing that you see. So the other thing you see is that if I do math problems, I get super excited about the math. I was here trying to teach you how to do GCDs. And yes, that's correct. That's 45. Oh no, but we didn't read the problem correctly. Okay, well. Then you see, I have made a mistake already for today. The shame. Each candy bag costs $1.20. Please make sure you read the problems when you do them. Oof, is correct. I need to multiply 45 by 1.2. All right, how do you do this? So now I need to do 45 times 1.2. How would you do that? Well, here's how I'm going to do it. I'm going to first, I like a 90. I love multiplying numbers that end in a 0 by a decimal. So I'm going to divide the 1.2 by 2 and put the 2 into the 45. That gives me 90 times 0.6, right? So I just divided the 1.2 by 2, and then I get to double the 45. I get 90. That's equal to 9 times 6, and now you see that was the answer. Oops. Okay. But the answer was 54. So good. I'm glad that we have a very sharp chat who's watching here today. Thank you everybody for saving us, because I was like, how in the world do you get that? All right, next question. Okay, number 13, number 13. Let P and Q be non-negative integers for which P minus PQ squared equals 1 minus Q. If Q is not equal to 1, then what is the sum of P and Q? Ooh, that looks like fun. So I have to write this down first. Okay, I have P minus PQ squared is equal to 1 minus Q. So if I'm looking at this, I see some like nifty stuff that's true. I like factoring, okay? When I see something, my instinct is just like factor stuff. So if I have P times P minus Q squared, then I also know that P times 1 minus Q squared is equal to 1 minus Q. That better be true, right? Because if I just factor P out of both of these, it's 1 minus Q squared. Why does that make me excited? That makes me excited because there's this mysterious Q is not equal to 1. Why would I ever care about Q not being equal to 1? Well, it could be useful if I ever want to divide by 1 minus Q. You know, like one of the biggest rules in math is thou shalt not divide by 0, right? And so we cannot divide by 0, and 1 minus Q happens to be not 0. And this is also 1 minus Q times 1 plus Q. So that's nice. Now I divide by it. So that tells me that if I divide, oh yeah, the thing I just did super fast is I said that 1 minus Q squared is a difference of squares. It's 1 plus Q times 1 minus Q. And if you FOIL it out by multiplying, you can see that 1 times 1 gives you the 1. 1 times minus Q gives you a minus Q, but that cancels with the plus Q, and then you get minus Q squared over there. Okay? So in that case, I can divide by 1 minus Q on both sides, and that's going to give me P times 1 plus Q is supposed to be equal to 1. Oh. Well, now P and Q are non-negative integers. How is that possible? Oh. Non-negative integers. Oh, yeah. Non-negative integers include 0, right? So I guess if I have two things multiplying to be 1, I better have it be 1 times 1. I don't think I have any choice. It's got to be 1 times 1, right? So that means that P is 1 and Q is 1. No, sorry, 1 plus Q is 1. Right? So if P is 1 and 1 plus Q is 1, then I have P equals 1, Q equals 0. Now, a good thing to do here is to double check. So if I have P equals 1, Q equals 0, I've got a nice equation here. So let's go and try to put it in. So I have 1 minus, ooh, love multiplying by 0. So it's just 1. And the other side is 1 minus 0. I agree, it works. 1 is equal to 1, last I checked. So now I will remember to read the question properly. It says, what is the sum of P and Q? So the sum of P and Q tells me that P plus Q equals 1 plus 0, which is 1. All right, let's see if this is correct. Yes, it is. Next question. Number 17. What real number should be added to each of 2, 11, 21, such that the new numbers are 3 consecutive terms of a geometric sequence? Oh, nifty. So I need to have, I'm going to tell you how I think about these, okay? This is maybe a bit of an unorthodox way to think of these. But it's motivated by arithmetic sequences, all right? Here's a nifty fact, and I only first realized this nifty fact in graduate school when I was doing my PhD. Let me give you 3 numbers that are in arithmetic sequence. The 3 numbers, I don't know, what are they? 13, I always start with 13. 13, 17 and 21. Those are arithmetic sequence. Look at that. This is exactly halfway between those two. So it is true that 17 is exactly halfway between those two. Okay? But that's the same thing as saying 2 times 17 is equal to the sum of the other 2. Now the same deal works for geometric sequences. And the reason is because actually the middle one is the geometric mean. We just have to be a little bit careful. No, we don't have to be careful. It's all good. So, I mean, we always have to be careful. But what I was about to do, I was about to take a square root, but I decided not to. I'll keep it as a square. So if I had 3 numbers in geometric sequence, like, for example, let's just make up 3 random numbers in geometric sequence. Geometric sequence means you always multiply by the same thing. 4 times 3 is 12. 12 times 3 is 36. look at that. If I wanted to say that, these three are all multiplying by the same thing, here's how that logic works. From 12 to 36, that's like multiplying by a common ratio. And from 12 to 4, that's like multiplying by 1 over the common ratio. So the way you could think of this is that you have the numbers 12, 12 times the ratio, and 12 over the ratio. And because of that, what you see is that if you multiply together the two things on the outside, that's always going to be equal to the middle one squared. So if I ever have a geometric sequence, A, B, C, they're in a geometric sequence exactly when B squared is equal to AC. I want to use this. The reason I want to use this is because I'm supposed to add some real number to each of them, and now I know the middle one squared has to be the product of the other two. And that tells me that the middle one squared, which is 11 plus x, I add some unknown real number, squared, has to be the first one, 2 plus x, times the last one, 21 plus x. Everyone with me so far? This is the niftiest way to go and get these like geometric sequences. You could also try to say there's some common ratio and you could divide stuff. Actually, you get the same equations because the common ratio equation is 11 plus x over 2 plus x equals 21 plus x over 11 plus x. So that would be like cross dividing where I divide by this and I divide by one of those. But I always think of it just as like middle one squared is the product of the outer ones. All right, time to solve for x. So that's multiplying these things out. So I guess I wrote it this way. That's fine. So this is 121 plus 22x's plus x squared is equal to, now we FOIL this guy out. And what I just did here is this a plus b whole thing squared is the a squared and the b squared and the 2ab in the middle. Over here we FOIL this out and we got 42 plus, so that was 2 times 21, 42. And I have 21 plus 2 is 23x's plus x squared. Ooh, the x squared cancels. So I don't even have to solve the quadratic equation. That's convenient. Bang, they're gone. And now I just have to, oh, look at that. There's a 22 and a 23. How much more convenient could it get than that? Thank you, Math League. So you have x equals, and I have to now subtract. Oh boy, this is hard. 121 minus 42. Well, if it was 122, I can subtract 42 because it ends with 2, right? 122 minus 42, that was 80. But just kidding, it's 121. So that's 79. Okay, do I believe it? Let's find out. Always check your answer. If I've got a nice number 79, just try it. So 79 plus 2, I love it. 79 plus 2 is 81. 81 makes me happy because that's something I could possibly multiply or divide stuff by. So one of the numbers is 81. Next, 11. What's 79 plus 11? 90. 81. Where should I write these three numbers? Well, I guess I'll write it here. 90. And 79 plus 21, oh, that's 100. Do I believe that 81, 90, and 100 works? Yes, because to go from 81 to 90, you multiply by 10 over 9. And then you multiply by 10 over 9 again. It's all good. And therefore the answer is 79. Let's see if this is the answer. Oh, and I see that people are commenting in the chat. Yes, the common ratio is 10 over 9. We're good. Okay, let's do more problems. Get a drink. In a box, there are several blocks, all of which are different and either red or blue. There are 219 ways to select 2 blocks of the same color from the box, and 216 ways to select 2 blocks with different colors from the box. How many blocks are in the box? Tongue twister. So I guess I have some reds and some blues. Let's just say R is the number of reds, and B is the number of blues. R and B. Okay. Now, when I look at a question like this, I say, picking 2 blocks of the same color, I'll have to do some addition. I'll have to multiply some stuff and add some stuff, because it could be 2 reds or it could be 2 blues. That sounds hard. But what if I want to do the other one? 2 blocks with different colors from the block, from the, these tongue twisters. 2 blocks with different colors from the box. Well, I've got to pick a red and a blue, right? So now I know that R times B is equal to 216. Okay. But here's what I want to do now. You know what? If I'm going to just pick 2 boxes, I was going to say 2 boxes from the same block. No, if I'm going to pick 2 blocks from the same box, then that's just the total number of ways. It's going to be 219 plus 216, right? Because that's just what that would mean. If I pick 2 blocks, it's either going to be same or different. So actually what that tells me is that if I take, let's write it here, red plus blue, choose 2, that's equal to the sum, 219 plus 216. Do I actually want to do it this way? That also looks unpleasant. Okay, so I'll say, I thought that would make my life easier, but that actually looks also unpleasant. I'll have 2 equations and 2 unknowns either way, and that one, I'm going to have to do like R plus B and multiply them together. Okay, I'm not going to do it that way after all. I will go back and say, what does it mean 2 blocks of the same color from the box? Well, okay, 2 blocks of the same color from the box, that's also choosing 2 reds plus choosing 2 blues, that's equal to 219. Okay? So these are my possibilities. Although I'm also looking at this problem and saying, a bit of me is wondering if guess and check is the most efficient way to go. And the reason I'm saying this is because, okay, there's an interesting fact here, which is what I'm about to use. The number of reds and the number of blues should be about the same. So the way I'm saying this is because 216 and 219 are pretty close. And there's some, okay, so let's solve it first and let's see how this comes about. Well, do I want to do it that way? 216, do I really want to factorize 216? I'm trying to think to myself how much work there is to go and find 2 numbers and guess and check. It might still be easier that way. Yes, indeed, it might be easier. So 216 is 6 cubed, okay? Oh, maybe I didn't say yet. This notation just means the number of ways to pick 2 things from R things, okay? So now 216 happens to be 6 cubed. That's 2 cubed times 3 cubed. Now, the square root of 216 is around 15. The square root is around 15. And I know that because 15 squared is 225. And I'm telling you, I have an inclination that somehow R and B are quite close together, and I'll explain why after we're done with this problem. But that means I want to find R and B, which are close to 15-ish. And one thing I can see is I could make an 18. I could make 18 and... Is that what I want? 18 and 4? That doesn't sound very exciting. Wait, did I do that right? So I could make 9 times 2. Yeah, I could do 18 and 4. That's one way to split this. I could also do 9 and 8. Oh, yeah! Those are much closer. What in the world am I talking about? No. Something's fishy. 8 times... Wait. It's 6 cubed, right? And 6 is 3 times... What did I do? What did I do? I wrote the wrong thing. It's 6 cubed. Yeah, there should be a cube here. Okay, that's important. All right. So it's 6 cubed. So if I have 6 cubed making 216, right? So that was a typo. Sorry about that, guys. And so now if I want my 18, now I can see a better number. Because if it's 18, I'll use 2 of these guys and 1 of those. And I could get 18 and 4 times 3. 18 and 12. I could make 18 and 12. Right? So I'm actually going to try 18 and 12 first. And if it was 18 and 12, what would happen to the 219? So what does 18 choose to? That's equal to 18 times 17 over 2, because there's 18 ways to pick the first one, 17 ways to pick the second one, divide by 2, that gives me a 9. 9 times 17, what's that? Well, that's like 170, but just kidding, you got to subtract 17 out of that, so that's 153. A bit of me is always scared, what a weird big number, but double check that by adding the digits together and seeing if it's a multiple of 9. And 1 plus 5 is 6, 6 plus 3 is 9, checks out. And I said it was 18 and 12 could be the possibility. 18 and 12, just double checking. That would be 2 of these and 1 of those, that's 9 times 2, that's 18. Or 2 of these and 1 of those, that's 4 times 3, that's 12. 12 choose 2, that's 12 times 11 over 2. Good, so cancel that out, that's 6, that's 66. Ooh. Look at that. 3 plus 6 is 9. 15 plus 6, that's 21. Aha! So then this thing tells me, bam! That means there's 18, well, I don't care if it's reds or I don't care if it's blues. It's 18 of one kind and 12 of the other kind. Okay? So if you look at this, this actually does work. That's the number of ways to pick 2 of the reds and 2 of the blues is 219. And the number of ways that you could pick 1 of each is just 18 times 12, which is 216. And the answer would then be 18 plus 12. And that's 30. So I need 18 plus 12, the total number of blocks in the box, and that's 30. Let me first check the answer before I go and start telling you how I guessed that they were really close together. It is. Okay, so this is good. Now, how in the world would I have guessed that they were so close together? You see, I was going based on these two being close together. And there's a way to think of this, all right? The way to think of this is that I have a lot of people. Some of the people are in a red room. Yeah, some of the people are in a red room. That's the closest color I've gotten to red. Then some people are in a blue room, okay? And they're people. Here are people. All these people. I guess these are also like blocks in a box, now that you think of it. But I just like to think of people. I like people. So I got all these people, right? And so what's going on here is, yeah, you're right. We could have said x is the whole number of blocks, but the problem is how would you use the information? You see, because one of the informations is you multiply 2 of them together and get 216. And so if I was doing it that way, I would end up with 2 equations and 2 unknowns, and I didn't really feel like solving some horrible bunch of quadratic equations because that's like r times r minus 1 over 2. Yuck. Yuck is the only thing you can say there. It's awful. It's awful. So I said I'd rather just factorize out and try to guess and check. But in that case, somebody said, you could just call these guys Jack in the Box. That's you guys are clever. But if I look at this, actually, what's going on is I'm sort of counting the number of handshakes. It takes 2 hands to shake hands. And there are some kinds of handshakes which are between same people, like people inside the same box. Jack in the Box is inside the same box. And then there's also another kind of handshakes that goes between the boxes. Between people in different boxes. Feet shakes also you could do. It's just that feet, it's harder. I think you have to be a chimpanzee because we don't have opposable thumbs on our feet. So I think it's a little bit harder to get a good firm handshake. But now when I look at this thing, okay, there's something interesting about graph theory. This is in an area of math called graph theory, which is actually what I think about all day. And in graph theory, if you actually take a bunch of people and you split down the middle, if you had a ton of people, like tons and tons and tons of people, if you had so many people, like, I don't know, let's say you had so many people that there were n of them here and n of them over here also. I'm saying, what if they were equal? If you had them both being equal? Well, first of all, this is related to an inequality called the arithmetic mean geometric mean inequality. I should probably not call these both n. I should say half of them. If you put half of them on each side, okay? It turns out that if you imagine having n people, splitting them into 2 pieces, 2 groups, then if you want the most number of cross handshakes, that happens when you have the 2 of equal size. And that makes sense, because if you had like n people and you were like, hey, you know what? Let's put all n of them over here and put nobody here. Well, then how many cross handshakes do you get? 0. And if you move on from like everyone and no one to like most people and some people, well, then you start getting some handshakes across until you get equal. Then you get exactly n squared over 4 handshakes across. If equal, n squared over 4 handshakes across out of n choose 2 total. Now here's the interesting thing. When n gets big enough, when you have a big n, if you want to know what is n choose 2, well, that is equal to n times n minus 1 over 2, which is like sort of n squared over 2. Like sort of with like a pretty, pretty ambiguous sort of. It's like, sort of. Because this is n minus 1 and it's not n, but it's sort of. Yeah. But the point is that if you go over here, that's half of this. What I'm trying to emphasize is if you actually had like a ton of people and you just split these into two groups, then if the groups are equal size, it's basically half of the total number of handshakes that happen. And why I wrote all these squiggles is because as n gets bigger and bigger and bigger, as a ratio, the ratio of n minus 1 to n, like my percent error, goes to 0% error. Okay? So the important thing is, if you see that your number of handshakes that are going across is roughly the same-ish as the number of handshakes that are within the sides, then that means that your split is almost 50-50. So that's actually how I knew which one to guess first. Because when I looked at the problem, I said, aha, the problem has a 219 and a 216. And those are so close together. And so since those are so close together, I should go and start off by finding the closest possible split of 216 into two parts. And that's when I looked at this and I said, well, 216 is like 15 squared-ish, so I want some numbers close to 15. And I saw that I could make an 18 out of these like 2, 2, 2, 3, 3, and 3. So that's how we started with the 18 and 12. And what I was doing in my head while I was looking at the 18 and the 12 is I was thinking, can I find anything closer together? And I couldn't find anything closer together than 18 and 12, so then we just did it. And it worked. Okay, we should do more problems. Next question. Oh, I should say, if you like this stuff of what we just did about graph theory, if anyone wants to, my class in Carnegie Mellon University is live streaming for free on my YouTube channel. It's running Monday, Wednesdays, and Fridays at 2:10 p.m. Eastern. And we will start on Monday, in 2 days, an entire section on graph theory, which is all about this stuff. Okay, next. Problem 19. Point A is 10 units away from the center C of a circle with area 2 pi. Two different lines tangent to the circle are drawn passing through A and intersect the circle at B and D. Find the area of the quadrilateral ABCD. Well, let's start by drawing a circle. So I'm supposed to have a circle. Let's pretend that's a circle. And that's the center is in the center. Okay, so there's a center here, that's C. Now, there's this point A, which is 10 units away. Okay, 10 units away. Don't know where it is, but let's call it there. And that's 10 units away. Next, I need to draw two different lines tangent to the circle, passing through A and intersecting at B and D. Okay, I think that looks something like this. So I have to have some tangents, maybe this one. The thing about a tangent, by the way, is that it comes in with a right angle. And here's where my freehand circle isn't great. But I already know that this is a pretty symmetric picture. So it probably looks something like this-ish. Pretend that those were right angles and those were straight lines. But I've got that. And these are B and D. Hooray! Now I've got this picture. And I have one more piece of information. The center C is of a circle with area 2 pi. And so area is pi r squared. Therefore, the r has to be square root of 2, because it's pi times r squared to get the full area. Now I've got two of these guys, which are square root of 2. Hey, it looks like it's Pythagorean theorem time. So if I have the 10, and if I have a square root of 2, then what's this thing? Wow, 10's far away. Just doing a quick check, does this make sense? Yeah, it does. Because if this is square root 2, actually, this a should be like way past my head out the other way. Because if that's only 1.4 units, 10 units is like over there. Okay, but we can Pythagorean theorem. This guy is going to be the square root of 10 squared, which is 100, minus root 2 squared, which is 2. Oh, these are fun. Root 98. Now I see what you're doing, Math League. Root 98. Can you simplify that radical? Well, yes, you can. Because 98 is 2 times 49. So that's square root of 2 times 49. But I know what's the square root of 49. That's 7. So it's 7 root 2. Suddenly, what I've got is I've got a root 2 and a 7 root 2. And I need to find the area of the quadrilateral. Well, it's half base times height times 2. Then forget about the half. Just do base times height. Right? Because it's like, you could even imagine you grab that guy, flip it around, put it here, complete a rectangle, and the answer is just root 2 times 7 root 2. That's going to be 7 times 2 is 14. So I just have root 2 times 7 root 2, and that's 7 times 2, and that gives me an answer of 14. Let's see if this is correct. It is. All right. Next question. Number 21. Ooh. Wait, who's been programming here? There's like some computer programming language where this is actually true. What's that programming language? Is it Python? I'm trying to remember. I program in a bunch of different languages, and I've seen this in one of them. My gut feeling is this is Python, but please correct me if I'm wrong. Oh, we got people here who know. It's Python. Okay. Oh, people said no? Ah, double slash means comment, depending on what you're doing, right? Oh, yeah. If you go and put that symbol in C++, you may as well forget about what's on the rest of your line. But it's the integer. I think this is integer division in Python. All right. So this a divide b is the greatest integer less than or equal to a divided by b. Let d and l be randomly chosen integers between 1 and 100 inclusive. What is the probability that if I take d divided by 4 round down plus l divided by 4 round down is equal to d plus l, and then divide by 4 and then round down? Oh, this has something to do with carrying. Okay, so that's neat. Now the thing about this problem, when I'm looking at this, I'm like, well, there's going to be something important about 4s. But I don't think that I'm going to have to care too much about the fact that it's 100, because I think that things are going to end up repeating. And here's what I mean. Actually, if I put in, it is exactly this. So notice that if I do d /4 plus l /4, well, let me not use d and l. Let's use exact numbers, okay? Because that will make it more easy to understand what I mean. Suppose I had 7 /4 plus, I'm making up something, like 23 /4. Suppose, let's put a question mark. I don't know if it is or not, but like whether it is or not, equal to 7 plus 23 /4. Well, the truth of that, whether it's true or not, is exactly the same as if I just added 4 to the 23. That's why I used a color here. So I'm going to write the same thing again, 7 /4 plus, now I'm going to flip the 23 to a 27. All I did is plus 4. /4, is it or is it not equal to 7 plus 27 /4? These are really interesting questions, by the way. First of all, do people buy what I've just said? What I've just said is, why would the truth be the same between these two? It's because if I look at what I did to the left-hand side, I know that the left-hand side went by +1, for sure. Because this /4 is just you divide by 4 and you throw away the remainder. And the 23 and the 27, they have the same remainder because, dividing by 4 and I just moved by 4. And over here it's also the same remainder because 7 plus 23 has the same remainder as 7 plus 27. Is that okay with people? So what I've just found out here is that if I shift the L by multiples of 4, it won't change the truth of the answer. And that's when I'm going to say, who cares about between 1 and 100? I claim that the answer is the same as if I just let d and l be randomly chosen integers between 1, 2, 3, 4 inclusive. That's how we're going to save a ton of work. And the reason is because it's like it repeats. If I imagine that I drew some kind of a diagram being like, maybe I can draw it this way. The d's being 1, 2, 3, or 4, and the l's being 1, 2, 3, or 4, I'm drawing some kind of a diagram where I'm just saying, like, is it true or not? Right? Is it true or not that this thing is equal to, right? I'm trying to find out, is that equal or not? Well, at 1 plus 1 is definitely true. Sorry, at 1 and 1 is definitely true, because if I take 1 divided by 4, round down, that's 0. 1 divided by 4, round down, that's also 0. And then 1 plus 1 is 2, last we checked, and 2 divided by 4, round down is 0. Okay, so that's a true. But by the way, some of these are false. If I go up to the 4 and 4, you know what happens? If I did 4 /, that's also true. So the 4 one is also true, because it's like 4 /4 is 1, 4 /4 is also 1, and now over here, that's just going to be 4 plus 4, that's 8 /2 is also 1. That actually makes me very unhappy because I wanted to show you some nice geometry, okay? We'll get there. But I want to say some of these are false, all right? So suppose I had something like, like the 3 and the 1. I just want to show you that some of these are sometimes false. If I have the L be 1 and the D be 3, well then I have 3 /4, that's 0. This over here is 1 double slash 4, that's 0. But over here I have 3 plus 1, that makes 4. 4 double slash 4 is 1. And 0 plus 0 is not 1. So this is a false. Although actually maybe it's not bad this way. Is it bad this way? Yes, it's bad this way. So anyway, so I first want to tell you some of these are true, some of these are false, okay? But if I know the answer for this pattern of 1, 2, 3, 4, if someone wanted to know, hey, what happens if I allow this guy to be 5? Well, actually, let's not do it that way. I'm going to say that was 1 unit, like this. Let's keep going. 5, 6, 7, 8. My claim is that you'd get the exact same picture. Is that clear to people? It's like whatever picture I have here, it's going to be an exact copy of it here. Because all that happened is for each one from this spot to that spot, the D went up by 4. And this D goes from 3 to 7, and it's the same L. And by the way, it's the same picture going down. It's like, maybe some of you have these floors. Like if you look at the floor that you are standing on, if you have carpet, it doesn't look very interesting. I'm on carpet. If you're on hardwood floor, you also can't see it. But sometimes you have these like nice patterned tiles. And what I'm saying is that you've got these like 4x... Yes, that's right, Daniel Guo. It's like tiling. I have these like 4x4 tiles, which are just repeating. And that's why I got super excited that 100 is a multiple of 4. So I just have like perfectly 25 of these pictures going across, and it's like 25 of them going down, and all I care about is what's the fraction of truths. So let's just focus on one of these tiles, right? That's all I got to do. I just have to go here and figure out what is going on in here. Okay, now here's the deal. If you're doing something with these floor tiles, actually, if you've looked at your floor enough, if it is really like this repeating pattern every like 4x4, I don't actually like going 1, 2, 3, 4. I like going 0, 1, 2, 3. But my claim is that the fraction is the same. It's like if you had this tile floor that was like tiling in these patterns, and it didn't have like thick lines, so you were like, those are the places where you cut. You don't know where you cut. You can cut anywhere. If you could cut anywhere and say, I will now go and make patterns where I just go across from here, and it's the same thing. And so I prefer to cut with the 0, 1, 2, 3. And you'll see why. So the 0, 1, 2, 3 is going to give me a nicer way of seeing the TF picture, okay? So, what was this? This was D double slash 4 plus L double slash 4 equals, or not, D plus L double slash 4, okay? I claim that using 0, 1, 2, 3 is just like better. D can be 0, 1, 2, or 3, and you can even think of those as the remainder when I divide by 4. And I've got the L, which is going to be 0, 1, 2, and 3. Okay. Now you know in the real problem it was like there was a 4 thing here, but this strip of the 4 thing just got teleported over to there. It's sort of like one of these video games. Not sure if you've ever played this video game before, where there's like these like rocks that you're trying to shoot, and you have this this ship which can shoot rocks, and then when the rock blows up, it becomes 3 other like rocks, and it's called asteroids or something like that. And in that game, if you go around the end, you kind of go back over there. You fly around the other side. And if you go up to the top, you flip around to the other side as well. So that's exactly what I've just done. I've just taken this 1, 2, 3, 4, and I pulled one of those strips over here, and then I pulled the other strip from here up. But it's the same thing. Okay? So now let's finish this off. Oh, you had a Code and Asteroids game for Python. That's awesome. Okay, well, let's go and finish this thing, right? So now I want to do it here. The reason why this is fun is, can anyone tell me what D double slash 4 is? For D being 0, 1, 2, and 3? I claim it's not very interesting. I chose 0, 1, 2, and 3 on purpose. What happens when I do 0, 1, 2, or 3 double slash 4? Divide by 4 and round down? Oh, it's just 0. Yeah, this is like super easy. Because look, if I look at this 4 and those 4, the D double slash 4, that's always 0. It's just 0. And how about the L double slash 4? Same deal. L double slash 4 is equal to 0. Well then, I'm just wondering, when is the right side equal to 0? This is easy to explain. As soon as D plus L reaches 4 or more, it's not 0. Okay? When D and L are such that D plus L is less than 4, well, then it's going to round down. And that's what gives me a beautiful picture. How do I get the D plus L to be less than 4? Well, 0 plus 3 is still less than 4, but look at that. Once I go with 1, now that's it. 1 plus 2 is 3, which is less than 4. And the moment you go over, oof, 1 plus 3 is 4. And if I had D being 3, L being 1, the D plus L is 4. 4 double slash 4 is 1, which is not 0. Okay? So in that case, I claim it's a beautiful picture. 2. 2 plus 1 is still 3, not yet 4, but it becomes 4 next. And if 2 plus 2 was 4, 2 plus 3 is more than 4. Okay? What am I drawing? Oh, it's nice. This is just going to be like a triangle. Okay, and that's the case when this is true. So it's just a triangle. And now the question was asking me what fraction of them are going to be true. That was all the question asked. Well, I already got one wrong by not reading the question. Let me look again. Probability that it's equal. Yeah. So I just have to go and find out the probability that I have a true. And it's like, look at that. It's beautiful. How many things are here? There's 10. 1 plus 2 plus 3 plus 4 is a triangular number, one of our favorite numbers. And that happens to be 10. If you didn't see that, another way to see it is you say, hey, grab this 1, put it there. That's 5. Grab these 2, put it by that 3. Now I've got 5. 5 times 2 is 10. And then you can call yourself Gauss. Well, except that Gauss did it when he was 5. But anyway, and I couldn't have done it when I was 5. I was not Gauss either. But anyway, there's 10 of these things. There's 10 truths, right? So the answer is 10 truths divided by how many things altogether is 16. That simplifies to 5 over 8, and that is my proposed answer. All right. Let's see if this is right. Maybe I got it wrong, but let's see. Here we go. Bam! It's 5 over 8. It works. Okay, then that means we can go back and take a victory lap. What in the world just happened? The key thing here was we did 2 major steps. One of the steps was observing that it's a tiling pattern that repeats so that we don't get overwhelmed by the 100. And the reason you know it will do that is because I'm dividing by the same thing, 4, 4, and 4. If I was dividing by different things, I'd need to do some kind of LCM, GCD type business to deal with that. But now that I knew it was this, if you notice, I got unhappy when I wrote the T there, because I was like, actually, there should be some nice way to think of this, because this is basically telling you, did you carry when you added the numbers together? Did you carry in base 4? It's one of those things. And so then the question becomes, oh, how does carrying happen? Well, it comes from the 0, starting from the 0. That's when I did 2 shifts. And then we got to this, and we got 5/8. Somebody just gave me a time warning, 8-minute warning. That means we should do the next question. Because as you can tell, I'm having too much fun trying to explain to you why these are really, really nifty problems. And, we aren't doing all the problems in the mathleague.org collaboration because they just have too many really good problems. But I had a team of actually students who went and picked out some of what they thought were the most interesting problems that they wanted to challenge me with. And so that's what we're doing here. Next question. Whoa. When unfolded, an envelope has the shape of a pentagon. It does. When the lip of the envelope is folded over, the envelope has the shape of a rectangle. That is also true. The unfolded, and let me first draw for you, You've Got Mail. It looks something like this. Right? It's the mail app. Something like that. That's the envelope, okay? Now, I will know the unfolded pentagon is composed of rectangle ABCD and triangle AEB. Okay, I'm a bit regretting not drawing this bigger, but let's see. So ABCD, and this triangle AEB, that's telling me I want to go this way. Okay, drawing the picture is the first part, which is very important. So reading again, I've got a rectangle, ABCD, and whenever someone tells you the letters, they're reading the letters consistently. You don't jump over a spot when you name the letters. And then the other one would be AEB, all good. Where E is outside the rectangle, yes, and AE equals EB, yes, like any good envelope. If the perimeter of AEBCD exceeds the perimeter of ABCD by half, what is the area of the envelope when unfolded? Oh, okay. Oh, I have some lengths, good. AB is 2 and BC is 1. Hey, that actually even looks right. 2 and 1. I was actually trying to draw a legit envelope. Okay. And now I know that the perimeter exceeds the perimeter of ABCD by 1. Well, the perimeter of ABCD, by half. By half. Now I'm trying to figure out what the question means. Because there's two ways to interpret this half. Is it like I take the perimeter and I add the number half? Or is it that I add 50%? We'll compare, because I see a common fraction. And the good news about this is, since we're going to be discussing the lengths of these things, if it's the wrong way, it's going to end up having a square root. Because if I have the hypotenuse being some nice number, but then if I look at the areas, I'll have to figure out this height here, which will involve some square root. So we'll soon find out. My gut feeling is if it says exceeds by half, it's like it's 50% bigger. But then let's try. So let's try the 50% bigger first. So first of all, the perimeter of ABCD is going to be 2 plus 1, which is 3 times 2. So half of it is 3. If half of it is 3, that means that each of those is 3 over 2. That's one possibility. And what does it mean to exceed by half the other way? Wait. No, that's not what I want. That's not what I want at all. This is wrong. So it's not the 3 over 2. It's not 3 over 2. Because I actually have to say I replaced a 2 by that. Okay? So I actually upgraded a 2 into a 2 plus 3. So that becomes 5 over 2. Did I do that right? Now I'm afraid of doing things too fast. So effectively what happened is that the half would be 3. So if half of the perimeter is 3, and I'm supposed to have that the pentagon has 3 bigger total perimeter, I need to upgrade the 2 into a 5. Actually, that's correct. So each of these becomes 5 over 2. Okay. At first I was like, I wonder if it's a 3, 4, 5 business. But the 3, 4, 5 business, that doesn't look quite right. Because now I need to read the problem again. When the lip of the envelope is folded over, it has the shape of a rectangle. Okay. We got the unfolded pentagon. It's the rectangle. Okay. AB is 2, BC is 1. I've got this triangle. They're equal lengths. And if the perimeter is bigger, then, yeah. Okay, just double checking. What's the perimeter? 5 plus 2 is 7. 7 plus 2 is 9. And 9 is half bigger than 6. Okay. But this would give me a funny radical. Because if that's 5 over 2 and this is 1, then I'm going to have some kind of a funny radical. So I'm going to try something else. Now I'm curious. I wonder if the half means just plus half. So I'm no longer happy with the 5 over 2. Now I want plus half. So if it's going to be that it's going to change from 2 into 2.5, oh, this actually will work. Okay, I see what happened. This is really additional half, plus half, right? Because what has to happen is from this 2 into this bent thing, I need to become 2.5, which is 5 over 2. That means each of those is 5 over 4. Now I like that. That's because I like the number 5. 5 gives me something like a 3, 4, 5. Now I'm going to write on the next screen this bigger picture. I think we're good now. So what actually happened is I have this rectangle, 1, 2, and 1. And the 2 I'm already breaking into 1 and 1. And then I also have this piece which is here, probably something like this. This is 5 over 4 now. That's what we had. And you see why I did it. It's because the problem kindly said common fraction. So if we want a common fraction, then if that's 5 over 4 and that's 1, this is a quarter of a 3, 4, 5. So that means that this is 3 over 4. Because you see, 1 is 4 over 4. So 4 over 4, 5 over 4, 3 over 4, that's a 3, 4, 5. And the question asks, what's the area? The area when unfolded. Well, the area of this part is 2 times 1, that's 2. And the area up there is half of the base times the height. That's half the base, and that's the height. So 1 times 3/4, the answer is 2 3/4, but I need a common fraction. So then I put over a 4. 4 times 2 is 8, plus 3 is 11. And that gives us 11 over 4. Let's see if that's right. It is. And with that, I think we just about ran out of time. So what we're going to do is we're going to continue these problems again tomorrow night, 8 o'clock p.m. Eastern Time, same place. And hopefully you had some fun. I certainly did. I'll see you then. Take care. Bye-bye.